Here is a problem of interference, an example that we're going to solve not using the approximation of the small angle. All right. So we have a car that is traveling horizontal to the plane of two antennas that are emitting the same signal. The antennas are 300 meters apart, and when the car is 400 meters apart, it receives the second maximum. All right. So which means m is equal to 2. And based on this information, we want to find the wavelength that is being transmitted by these antennas. Okay, it says here, do not use a small angle approximation. So what we're going to do is we're going to actually use geometry. Okay, so first of all, let's see what is given to us. M is equal to 2. And the distance between the two antennas or the sources is 300 meters. And the distance between the point P, vertical distance between point P and the antennas is 1,000 meters, and the x2 is 400 meters. Remember the distance from the center to the second order of a maximum. All right. What we want to find is the wavelength. Okay. So what we do is, since we cannot use the approximation, what we're going to do is we're going to use some geometry. Okay, so I'm going to draw a line here that is perpendicular to the plane of the antennas, and then I'm going to draw the two paths that the signal has to travel. So this is at R2, this is at R1. Remember, this is, so here's what we have now. We have two triangles, this one here to work with, and this one here to work with. Okay. So remember what we need. We need to find what delta R is, which is very simple. It's R2 minus R1. However, to us, it is given that this is twice the lambda, since it's the second maxima. All right, so that's the equation we have to start. So we're going to use some geometry to find R2 and R1, and more exactly, we're going to use Pythagorean theorem. All right. So what we have is, so if this is, again, this is D, this side of the triangle is x2 minus D over 2. Okay. And we can actually put numbers. And the other side for the bigger triangle is x2 plus D over 2. All right. So pretty much you can see we know the sides. We're trying to find the hypotenuse. So we have R2 squared is equal to 1, and we can write D squared plus x2 minus D over 2 squared, and R1 squared is equal to D squared plus x2 plus D over 2 squared. All right, we're not going to try to derive an equation. We can use numbers here. So let's see that x2 minus half of D happens to be 400 minus 150, and that is 250 meters. And x2 plus half, that is plus 300, is 550 meters. And of course, we have D to be 1,000 meters. All right. So we can find R2 to be square root of 1,000 squared plus 250 squared. Sorry, that's R1. I apologize. These are 2 and 1. R2 is the longest one. Now, not that it will matter. And R2 is square root of 1,000 squared plus 550 squared. So what we're going to do now, we're going to calculate them, and then we'll figure out what so to cut it short, 4 and 5, we're going to figure out what the wavelength is, which is R2 minus R1 divided by 2. Okay, that's going to be our final equation. So now all we have to do is plug in the numbers and figure out what the wavelength is. So let's just put them into the calculator, and then I'll pause the video, and then I'll start when I have the calculations done. So once we did the calculations, we found the lambda to be roughly 55 meters. All right, so the wave length transmitted by these antennas is 55 meters, radio waves that is, okay? So to the answer to the question, where will be the next, how far does a car have to travel to find the next minimum? So remember, this is the maximum, the next one is the minimum. The distance between them, this distance here is actually half of wavelength roughly. All right, so which means the extra distance that the car has to travel is half of wavelength. So that extra distance is actually 27.5 meters. Okay, so that's how you solve a interference question without using those small angle approximations. On the next example, we'll actually use the approximation.